Dear professors, honorable chair of the conference, I am extremely grateful today and I would like first to dedicate a special thanks for your time devoted to lead this conference under the best circumstances and for giving us the chance to expose our works. I am Elmouzoun Elidrissi Mouad, a PhD student at Hassan First University of Sadat, Faculty of Science and Techniques, Radiation and Matter and Instrumentation Laboratory. My work's title is shown here, Automatic Drowsiness Detection based on a single channel of EEG signals using a hybrid analysis and a decision tree classification method under Python. So this work is under the supervision of my professor Harmouchi Mohammed and our laboratory team. So as a plan, we will start with an introduction followed by the problematic, the state-of-the-art study. Then we will expose our proposed method where we will show our results obtained, and finally we will conclude with a conclusion, of course. So we all know that the human brain activity is just a huge number of electrical signals for fulfilling our heads. So every thought, every movement, every eye blink, and even every feeling is just the translation of our brain signals. Furthermore, while driving, a complex connection of our brain signals is established, which can cause drivers to feel tired and even more so to feel drowsy and maybe sleepy while driving, leading to dangerous and deadly accidents. Here in this picture we are showing another factor that can make the driver feel sleepy, which is the monotony of the highways, and especially the fact that he or she travels long distances and drives for many hours. So we know that the city's accidents are more frequent than those happening in the highways, and a brief loss of attention on the highways can lead to serious and fatal accidents, which cannot be the case inside cities. So here in Morocco, the percentage of deadly accidents in highways caused by drowsiness behind the wheel is 33.33%. In other terms, one fatal accident on 3 frequency. And this has given us reason to reflect on the resolution of this grave tragedy and makes us ask ourselves this question: what kind of system can we develop to avoid this accident, and what are the most significant parameters that we can use to achieve our main goal? So after analyzing this problematic, the idea was to develop a system that can detect automatically the driver's state of drowsiness, which is the stage of transition from the normal and awake to the sleep state. Though the idea of this system is not new, but it will be a system that will help to resolve the limitations of the existing, of course. So our work is therefore to develop an intelligent system for the automatic detection of driver's drowsiness based on the analysis of the electroencephalogram, which are called EEG signals. So using a new, efficient, and a new accurate algorithm. So before all, the first step we have taken is to focus the study on some similar systems already realized with the same or different technologies, and to extract and identify their limitations. So here we are showing 2 types of systems, but they are based on the same technologies. So this system on our left is a smart glasses for detection drowsiness. It works by inspecting the frequency of the eye blinking due to an infrared sensor. It's a transceiver, also detecting the microfolds of the head using an accelerometer or gyroscopes, just like the cap on the right. But that's not enough to judge a driver's drowsiness state. So the limitations is that the systems are based just on microfold analysis, and no physiological parameters. And also they have a very low detection efficiency. So, the system here in the slide are based on facial recognition of the eyes or the face of the subject using a specified algorithm. The system on the extreme right is also based on the same technology, but instead of using a camera, it uses an infrared camera to inspect the respiratory frequency by capturing the temperature under the nose region. So they have many limitations which we can cite, that the results are not in real time. The systems are weak and ineffective in the absence or lack of the light for the first and second system on our left. In some head and face orientations, the detection of the face or eyes regions is not possible. So this following system is the one used in our work and the most important and efficient, which is based on the analysis on the physiological signals that are the EEG signals here, and especially a single channel for our method, which is the FP1 2 reference channel. Okay, FP1 2 reference. So we used this channel because different studies showed that the FP1 location of the electrode is the most used in this type of research, showing a high correlation to drowsiness detection. So the reference is the reference number 11. The steps of this type of systems are shown here in this slide. The first step is the signal acquisition, or the phase of preparing the datasets. The second step is for the pre-processing and filtering in order to eliminate the noise while recording. Then we have to prepare our main processing algorithm containing the whole analysis, the feature extraction, the feature selection, the training and the testing of the classifier, and finally the display of the results of our chosen classifier. So here our method is summarized in the following flowchart. For the two first steps concerning the data acquisition and pre-processing, we used an open access database, which is Physionet, that allows a free database for the future researchers working on the EEG signals. These databases are available, and they are artifact free, which means that the noise is filtered just after the acquisition phase. We modified the database in a way to analyze just the single channel of FP1, and we transformed the type from EDF to CSV file extension. After that, we reorganized the data in a vector shape according to our processing algorithm. So three domains were chosen to analyze the data: the time domain, where we performed a statistical analysis of the data using 8 main features extracted; the fast Fourier transform domain, where we analyzed the frequencies bands of the data; and finally the power spectral density domain, which represent the frequency distribution of the power of our EEG signals according to the frequencies that compose them. So these features will be fed to different type and architecture of classifiers chosen right after the reshaping of the features, of course, because we have to took the features as a vectors according to the input shape of the classifier. And finally, it comes the approbation step in order to check the validity of our algorithm and its confusion matrix values and the results. In this step, we took some new data which we know their labels already and fed them to our saved model to test if the prediction is correct or not. So that's the main overview of our method. In order to situate our work, the following works used a single channel study also. In addition, like our work, in addition to using the same dataset of EEG signals available at Physionet database. So, in order to compare our results and show the improvement added by our hybrid method. So, the first work of Belakhdar proposed a method of analyzing the spectral domain of the EEG signals under MATLAB by applying Fourier transform in the classification by artificial neural network. With this method, their work reached an accuracy of 88.8%. So it's the reference tree. In the work of Bajaj, they reached an accuracy of 81% after extracting the features and using the tunable Q factor wavelet transform from the EEG signals, and they used a classifier named Extreme Machine Learning Classifier, so ELM. The highest accuracy was which is 94.45% was reached by the fourth work after using a processing method based on wavelet packet transform WPT fed to the extra time classifier. And finally, the proposed work aims to improve the efficiency of the algorithms of detecting drowsiness of drivers based on a single channel of EEG signals in the term of rapidity, accuracy, and the processing time. So the conception of time of processing. So here in the following slide we are showing our results obtained. So the table on the left, the first one, shows the different classifier we used to train our model, where we used 8 classifiers for the first method based on just PSD domain. The second method is the FFT only domain. The third method we use the features of time domain only, and our hybrid method, our last column is our hybrid model using the decision tree classifier. We reached the highest accuracy of 98.7%, and the best processing time consumption is 62 milliseconds according to the second table. So in here on the right, it's a screenshot of the output of our model from Python IDLE used, showing the whole confusion matrix results, such as the precision, the recall, F1 score, and the classifier's accuracy. So to conclude our work, we extracted a total of 8 features from the 3 domains: the time, the fast Fourier transform, and PSD domain. After that, we trained 8 machine learning models: super vector machine with its 4 kernels, the Gaussian process, k-nearest neighbors, multilayer perceptron, and decision tree. We compared our work to the previous ones based on the same datasets available at Physionet and the use of a single channel EEG records. So the added value of our model is the improvement of the accuracy of detection. So we performed and improved the performances in the term of accuracy, which achieved 95.7%, and a processing time is which is 62 milliseconds. So this is the bibliography for our work, and thank you for your attention.